We are now going to look at the input and output common mode ranges of the telescopic op-amp as well as its slew rate. So let us look at the input common mode range. So let us assume that the input common mode is equal to the VCM in, and we want to find out the minimum and maximum values of VCM in. So of course, when you apply an input common mode, so you connect the two inputs together and apply VCM in. Now suppose you started reducing VCM in. So because the total current in M0 remains 2 I0 till M0 goes into triode, the two transistors M1 and M2 will continue to have a current I0 each, and therefore VGS1 and VGS2 will remain constant. So therefore the voltage at XY reduces. So as VCM in reduces, so the points we will make are ID1 and ID2 remain at I0 as long as M0 is in saturation. This means that VGS1 and VGS2 remain constant. And finally, this means that VXY follows the change in VCM in. So as VCM in is reduced, VXY also reduces till M0 goes to the edge of triode region. Therefore, minimum VCM in is reached when the transistor M0 is just at the edge of the triode region. At that point, the voltage at XY is VD sat 0, and so this is nothing but VD sat 0 plus VGS1. Just remember, VD sat 0 is calculated at a current 2 I0, VGS1 is calculated at a current of I0. Now next we will see what happens as you start increasing the value of VCM in. So now suppose we start increasing the value of VCM in. As you can see, you can follow the same set of arguments. So as VCM in is increased, you can say that VXY follows VCM in. And therefore M0 is actually moving further away from triode. There is no problem, and VGS1 and VGS2 stay constant. And both of them carry a current. Now please note that the voltage at the drain of M1, which we shall call VD1, is biased. VD1 is actually at a voltage equal to VB3 minus VGS3. Therefore, 1 equals VB3 minus VGS3, where VGS3 is calculated at a current I0. Please note that because the current stays constant, VGS3 also stays constant. Now, please note that for M1, VCM in, so the gate voltage is increasing, whereas this is constant at VB3 minus VGS3. So M1 enters triode when VCM in is one threshold voltage larger than VT. So in other words, so the maximum value of VCM in is VB3 minus VGS3 plus VT1. So the input common mode range, is VDSAT 0 plus VGS1, VB3 minus VGS3 plus VT1. So please note that the input common mode range is slightly different from that for the one stage op-amp. Now, what about the output common mode range? So let us again take the same op-amp, but now we are now going to see what happens. What is the maximum voltage at the output versus the minimum voltage at the output. So of course, as let us call the output common mode as VOCM. So as VOCM increases, you will find that M6 has a constant gate voltage VB5, whereas its drain voltage is increasing. M6 moves closer and closer to the triode region. And therefore, the maximum value of VOCM is nothing but VB5 plus VB6. Similarly, as VOCM decreases, you will find that the gate of M4 is constant and M4 moves closer to triode region. This means that the minimum value of VOCM is nothing but VB3 minus VT4. Therefore, the output common mode range is VB3 minus VT4, VB5 plus VB6. As you can see, this depends on VB3 and VB5 numbers, but in general, you will find that the output common mode range of the telescopic op-amp is smaller than that for the one stage op-amp. Naturally, because you now have larger number of transistors and you cannot support a large enough common mode range or swing at the output mode. Finally, we will look at the slew rate of the telescopic op-amp. So we are now interested in the slew rate. So to find out the slew rate, so we will now apply increments of delta VD by 2 and minus delta VD by 2 at the inputs. As you might imagine, the currents are now I0 plus delta ID by 2 and downwards, and I naught minus delta ID by 2 flowing downwards through M2. And these are the incremental currents. Delta ID by 2 and minus delta ID by 2 are the incremental currents through M1 and M2. Now what happens to these incremental currents? So these currents flow through the other transistors. So the current through M3, M5 and M7 is I0 plus delta ID by 2, and this gets mirrored through between M7 and M8 to give you I0 plus delta ID by 2 through M8 and M6. Now what happens to this current flowing through M2? That current flowing through M2 flows through M4 also. So if you were to find out the total delta IO, you do that by applying KCL at output node. You will find that delta IO is the total current leaving the node, should be the sum of the currents entering the node. The sum of the current entering the node from M6 is I0 plus delta ID by 2, and the current entering the node from M4 is minus of I0 minus delta ID by 2. So this is nothing but delta ID. So the current delta ID flows through the output. Now where does this current flow? Of course the output will have a load capacitance CL, and therefore this delta ID current charges the load capacitance. So therefore for the capacitance you write IC is dVc by dt times C. This means that the value of dV0 by dt is nothing but delta ID over C, and this of course for small signals is nothing but GM1 delta dt by CL. Now if you start increasing the value of delta VD, you will find that since M1 carries I0 plus delta ID by 2, the current through M1 increases and the current through M2 decreases. So as the magnitude of delta VD increases, so ID1 increases and ID2 decreases. Eventually two I0 current flows through M1 and 0 current flows through M2. So all the current has shifted into transistor M1. So in this case you will find that in this case let us write down the expression for the total current flowing into the output node. So that is delta IO. So if you were to apply a really large step at the input, so you would find that you would have a current 2 I0, you would have 0 current, therefore M2 and M4 would be cut off. This current 2 I0 flows through M3, M5 and M7, and this gets mirrored into M8 and M6. Again, if you apply KCL at the output node, it is clear that delta I0 is equal to 2 I0. This means that dVO by dt is 2 I0 over CL. Now if you were to increase the input step any further, the output cannot rise any faster because the op-amp can only source a maximum current of 2 I0. So this is termed the positive slew rate of the op-amp. Now you can apply a negative slew rate, you can apply a negative step to the op-amp, and in that case M1, M3, M5 and M7 are cut off, and so are M6 and M8, and M2 and M4 carry the full current of 2I0 and discharge the load capacitance. So it turns out that this is also equal to the negative slew rate. So the positive slew rate is equal to the negative slew rate for the telescopic op-amp also.